Thank you, Arnie. So, as the title says, we're going to talk about 10 SQL habits, T-SQL habits that can kill performance. And actually, it doesn't say 10, but that's what I have. I have 10. And first of all, a little bit about me. And as Arnie said, I've been doing this for quite a while. Two things I always like to point out. I started with SQL Server 4.21a, and my first PC had a 10 megabyte hard drive. And that just points out how old I am. Yeah. You're right. My first computer did not have a hard drive. I had a little tape thing that. And we recently moved, and in the process of moving, you go through a lot of paperwork. And I uncovered a piece of paper. If you saw my session a few months ago, you've seen this. But I uncovered my first examination score report for SQL Server 4.2. And I have yet to meet someone else that has that old of a certificate. So first of all, about what we're going to talk about, I'm going to go through several things, discuss why they're bad, and show examples of how to do them better. And I do this for fun. As Arnie said, and I've said, been in the industry for quite a while, and I've learned quite a bit, and I truly enjoy sharing it with this great community. So feel free to ask questions as we go. I have my cards up here. If you come up with a question tomorrow or next week, next year, grab a card and ask me. Don't hesitate. I totally enjoy sharing what I know and learning new stuff. As Arnie said, the best way to learn something is to teach it, to present it. And so if there's something I don't know and you ask me about it, we'll dig into it. We'll find out. So what I've got is 10 different habits, and I've scored them in the 10 down to 1 mode. And I've tried to put them into an order where the first one's number 10 is less effective and less often seen, whereas I get down to 1, I see where it's very often I see it, and it can be very powerful. This is my experience. Your experience may be different, but let's go through them. So the first one is union versus union all. The union eliminates duplicates. So if you think about what happens with it when you do a union or a union all, it takes two result sets and it puts them together. With a union all, you're done. With a union, it has to eliminate duplicates, and in order to do that, it has to do a sort. A sort within SQL Server is one of the several iterations, the steps that SQL Server takes, the optimizer takes. Actually, the optimizer doesn't do it, it identifies it. And a sort can be very expensive. Each one of these I have an example. In this case, and I'm going to try out this new tool, and at the end of this session, I want you to tell me whether this is just a cutesy thing or really is helpful. And it does this thing like that. So, thank you, Arnie. So I'm using AdventureWorks 2016, and then I'm going to have two queries. One of them is a union all, and the other is a union. Other than that, they are identical, and we're going to look at the actual execution plan. Who looks at actual execution plans? It's probably the second thing that I look at when I'm performance tuning. First one is statistics IO, and I'll cover that in a minute. Actually, I'll cover it in a minute because it's off for this one. So I'm going to execute the setup and then execute the script, turn on the actual execution plan, and if you're not familiar, right up there. See, now I don't like this already. It's hard to move that around. Okay, right there is the button that turns on or off actual execution plan. So, see, this works better, I think. Doesn't that work better? Yeah. Okay. So turn that on. It is turned on. I'm going to execute it. They both will give the exact, well, they won't give the same results possibly, but one of them will have to do a sort. If there's any duplicates, then there'll be different results. But in this case, we'll look at the two execution plans. And a few things to point out. First of all, if you're not, yeah, I got it here. If you're not familiar with execution plans or the actual execution plans, or actually it's estimated also, when you have more than one query that you're including in the batch, the optimizer will give you its estimate of the percentage of that batch for each of those statements. So in this case, it thought that 44% would be taken up for the first one and 56 for the second. Take those numbers with a grain of salt. There's many things that will distort it and give you bad information, but this one, it's not that inaccurate. The important thing here is that we have clustered index scan, index seek. Everything's the same until you get to that guy right there. And there is that sort. And whether there's duplicates or not, it has to do the sort. It is almost always unnecessary. When I review code, it's amazing how often I will see a union, and when I look into it, it was just laziness. Somebody said, a union, it's quicker than writing union all, without considerations of whether it was needed or not. The second one is somewhat related, using superfluous order bys. I've seen many times with a query, just put an order by in there even though it did nothing. There's two types of queries that are intermixed. They're similar. There's a select into and an insert select. So with an insert select, the table or temp table already exists. You do an insert select, and if you do an order by with that, the order by is guaranteed, believe it or not. And the only effect that has is if there's an identity column on it, the order of your select will affect what the incrementing or decrementing of your identity column is. The other version, the reverse of that, select into. You do not have a table yet or temp table, and you select blah, blah, blah into from. That creates the table and populates it. It is allowed to put an order by on it. It does nothing. I don't know which version of SQL Server, I think it was 2005, was the first one that said, you know, because this order by does nothing, we're going to ignore it. But somewhere around that and prior to that, it didn't ignore it. It did a sort that ended up doing absolutely nothing. So anytime you have an order by, think about whether it's really needed, because sorts are expensive, can be expensive. And in this one, turn on actual execution plan. In this one, I'm using the Wide World Importers, which is another free downloadable sample database. And I have two queries, and I should compare the two queries and show you what they are first. Notice that they're exactly the same other than that one order by. Now that I've executed them, again, looking at the execution plan, that's the difference. Notice here, within this one query, that sort, the optimizer concluded or estimated that 98% of the effort of executing that query was doing the sort. Totally wasted. I'm having fun going back and forth with these two things. Not joining on keys. You know, all of these examples come from my experience. I have encountered these over and over again. Joining on keys is, again, a common problem. You don't always want to join on a key, but almost always, when you have a join, multiple tables, you want to join on the keys, whether it's a primary key or an alternate key or a unique index, almost always you want to join on keys. If you don't, you have the risk of returning multiple rows. And what do you do when you have multiple rows? Well, here's, in this example, I am going to run this query up here, and notice that we're joining 4 different tables. Yeah, there's 4 tables. And just looking at it, it's hard to see whether or not we're joining on the key, any keys or not. And when I execute this, I'll get 115 rows. And although this is on a demo database, this is almost an exact situation that I encountered not that long ago, where someone had not joined on keys, and his solution to it was exactly what I'm going to show you in a minute. But notice here, I think these are the rows. Yes, there's several duplicates, and I just highlighted one pair of rows that are exact same rows, and they are exactly the same. They're duplicate because you're not joining on keys. Is that a question?
So is that like, it's called join inflation? Is that what it is?
You know, I've never heard that term, but I like it.
Like when they do the joins, they told you it creates multiple records.
You know, really, I have been trying to come up with a good term for that. Join inflation. I like that. I really do. I've never heard it, but yeah, that definitely fits. You get extra rows that you didn't intend to get. So the developer sees that. Says, wait a second, I've got duplicates in there. Okay, anybody? How do you solve that?
Distinct.
Put a distinct on it. To me, not all. Again, all of these rules are. None of these rules are 100%. But to me, when I see distinct, that's a red flag. It's a swear word to me. Rarely is a distinct the appropriate thing to use. Not never, but rarely. So that's exactly what happened. Again, this is my example. You didn't see. Let's down here at the bottom. You can see there's 115 rows. Okay, and there's several or a few duplicates in that set. So the solution. Take the exact same query and just put the distinct keyword in there. What does that do? Well, that gets rid of the duplicates, but in the process of doing that, there's that nasty sort again. Because in order to get rid of duplicates, you have to do a sort. So what just happened? They got more rows than you intended. So you're processing more rows than you intended. That's going to hurt performance. And then you add this potentially expensive sort, and that's going to hurt performance even more. And finally, you get down to the right result set. But kind of a circuitous route to get there. So my habit, whenever I have one of these that I want to look to see if I'm really joining on keys, I will start putting out to the right. I'll comment out, okay, for this dim products, the primary key of that. Fact Internet Sales Reason has that. There's another one over there. And in so doing, I can see, look at that's the join predicate that was missing in that other query. The other that returned multiple rows and resulted in somebody adding a distinct. So now I can look at that and say, okay, now I'm going to join on the keys, and when I execute it, I get no duplicates, and I get the correct 108 rows. I start out with 108, not an inflated 115, and I don't have that expensive sort. Having too many joins. So when the optimizer is software within SQL Server, and its purpose is to take the query that you submit and figure out how to execute it. And one of the most important bits of information that it uses to come up with those plans or that plan are statistics. Statistics are summary information about how data is distributed within a column or an index. So when you're joining two tables together, you get the optimizer looks at the statistics of the join columns and other things, and comes up with a cardinality. That's the estimate of the number of rows. I'm going to get 500 rows out of here and 300 out of here. And then it's going to determine, okay, I'm going to do a nested loop join or some sort of join. And it has internal algorithms that say, okay, after this join, I expect so many rows out of the join. And then it might join to another table. If you have 5 tables that are joined, it doesn't do a single join of all 5. It joins 2 together, and then joins a third one in, and then joins a fourth one in. Each one of those steps, each of those join iterations adds more potential discrepancy or error in the cardinality estimates coming out of that join. The more joins you have, the more likely your estimate as you go down this path of the plan is getting further and further off. What does that mean? When the estimate gets off of the cardinality, the optimizer makes bad choices. It uses a nested loop instead of a hash or something, and your performance goes down the tube. That's one of the main reasons that having a whole bunch of table joins can be a performance problem. Is there a magic number of where? Absolutely not. If I have a query that's maybe 4 or 5 or more tables joined and it's a performance problem, I will probably look at whether or not having too many joins is one of the causes of the poor performance. What do? One solution, and there's others, one solution is to take some of the tables, join them together and put the results into a temp table. And then take the temp table and join it with the rest of the tables. You have 2 different statements. You don't have multiple paths that the optimizer has to analyze and potentially come up with worse cardinality estimates. You're limiting that error that it can introduce. There's also another thing about you hear the term best plan, and that's a misnomer. When you submit a query to the optimizer, its goal is not to come up with the best plan. Its goal is to come up with a plan that is good enough. And there's complex internal algorithms of what good enough is. But what happens is this: you submit a query, the optimizer says, well, let me try this plan. Okay, I've come up with so much effort to do it that way. And that's not good enough. Let's try another one. Right? And it keeps doing that until one of 3 things happen. 1, you run out of memory. That's rare and that's a serious problem. We won't cover that. Number 2, it finds a plan that it meets the threshold of good enough. It stops right there. It doesn't look at any more plans, and that's the plan that you're going to get. The third is it runs out of time. There's a time limit of how long it's going to spend looking for a good enough plan. If it hits that time limit, it says, okay, I've already looked at, 100 plans. I'm going to pick the best one that I've found so far. It's not within my range of good enough, but that's the best one I found, and that's what I'm going to do. Will that perform well? Maybe, maybe not. The point is, you want to try and avoid that timeout. And one of the causes of a timeout is having too many joins. The more joins you have, the more possibilities, the more permutations there are that the optimizer has to consider. And so that's one of the reasons. So in this case, I have, what do I have? I have a query that is joining several tables. No need to look into the complexity of the query, just the fact that it's joining a whole bunch of tables. And I just want to look at the estimated plan. And I didn't highlight something correctly. Invalid. Oh, maybe if I go into the right database, that would help. So I'm going to look at the estimated plan, and when we look at the plan, there's all kinds of information in that plan. You could study the plan for years and still find new stuff. So right here on the select, the leftmost is usually a select. Logically, a plan works from left to right. Physically, it's from right to left. I usually consider looking at it from the physical aspect, right to left, which means the last thing that it does is the select. Each one of these things is an iteration, and every one of them has additional properties that you can get to by right-clicking, and you get a context menu, and then you select properties. So when I look at the properties of the select, another window comes up, and right there I can see early termination. Reason is it timed out. Now, the plan that it comes up with may be a great plan or it may be lousy. I don't know. I don't want to take that risk. When I see that, I want to fix it. Rephrase. If it runs fast, don't worry about it. But sometimes it won't. That's one of the things to look at. When you see that, one of the causes of that is having too many joins. Overusing or misusing views. So views are wonderful things. The misuse of them is, in my opinion, prevalent. And they are easy to misuse. One of the reasons that they can be bad is they obfuscate the complexity. Another reason is, let's say we have in fact, in my example, I have a query of a view that joins several tables, I think 4 or 5 tables, about employee and person information. And in fact, let me bring it up and talk about it. So here's the plan, or here's the query. This is an existing view within the AdventureWorks database. And the human resources schema v employee view joins several tables. And it is, as the name kind of implies, it's information about employees. And there's other people in the database that are not employees. So I want to, for instance, I want to look at this view and say, give me the first, middle, and last name of all the employees. So because we have this nice convenient view here, it's like, oh, just use the view. Don't go out there and write a query that joins to the employee table and join that to the person table. Why do that? I get a view. It's nice and easy. Well, the problem with that is that the view joins other tables that aren't needed. And why do I have 2 queries here? Oh, okay, that's 2 different queries. So when I do the first one, and I'm going to show the actual plan. So notice that there's several tables joined there. So for instance, there's an email address in the center, person phone down at the bottom, and there's another one that I can't get to here. It is joining to those tables because that's part of the definition of the view. I don't need that information out of those tables. Those are totally unnecessary joins for this query. So this is a case where somebody designed a view to address a specific need, and then it's being used for other things. And that's a very common problem with performance. Here's another example. Here's a query. I'm joining 3 tables. Well, not really. I'm joining 3 views. And remember I said somewhere around 4 or 5 tables, I start looking at whether or not the complexity is a problem. Well, this isn't a problem because there's only 3, right? Well, let's take a look at it. So I'm going to just execute it. Look at the execution plan, and oh, it's running off the side of the screen. So you can zoom in to the execution plan and show more. So let's see, I'll zoom in. Actually, I want to zoom out. What am I saying? I want to zoom out, and then I'm still see more, zoom out. Okay. There's also a zoom to fit, so you can get everything there. Look at that. That's look like a simple query against 3 different views, not tables. But in fact, because each one of those views had a few tables that it was joining itself, that's the end result. And I don't think I have to say too much to say, well, wait a second, that's going to cause some performance problems. One of the worst things that I've seen in a view is somebody has a view and say, whoa, I can really use that information, but I need a little bit more. I'm going to create another view that also references this view, nesting views. To me, that is suicide. Just do not nest views. It obfuscates it, and you'll get this kind of stuff much more often than you want. Well, you never want it. Using user-defined scalar functions. Who uses user-defined scalar functions in a predicate? A predicate is one of those lines that evaluates the true, false, or unknown. It's like a where clause or a join clause, an on clause. When you use a user-defined scalar function in a predicate, the optimizer has no idea about cardinality. Remember, cardinality is, or the statistics which determines cardinality is one of the most important things the optimizer uses. It has to guess. The end result of the guess is often not a good result performance-wise. I have a scalar function here. This is, okay, turn on. I'm going to start with just showing you this one query. Simple query. I'm going to select from the factory sale or sales, and I'm going to use an internal function of the month. I'm just going to return the number of rows in the fact table that are in March. Yep, that's it. But this is a built-in function. It's not a user scalar function. It's a built-in function. So I'm not going to execute it now. I'm going to execute it in a minute and show you. But then I'm going to create my own user-defined scalar function. And all it's going to do is execute this built-in function. So it's going to do the exact same thing as the function. It's just embedded or into a user-defined scalar function. So I'm going to create that. Okay, so okay. I'm going to execute these two together, and they are nothing more than the same query, but one is using the built-in function, the other is using the user-defined function that I just created that does the exact same thing. And what did I do? I probably didn't run the whole thing. Now it'll work. Okay, a few things to note here. First of all, notice the plans. Right off the bat, you see that they're different. One thing to notice here, see that the execution estimate, where I said that ignore these in some cases, it's an estimate of how much effort this query is going to take compared to that one. The optimizer doesn't know about user-defined scalar functions, so it says, that's a nothing, so it's going to come up with 50-50 on this, but that's not true. In this case, that totally lies. Another thing to note here is the size of that line, and let me, I executed it. So, not that, okay, I'll get this right yet. So this is using the built-in function, and when I hover over that line, I get a very important bit of information comparing the actual number of rows to the estimated number of rows. Estimated number of rows is 5,071, actual is 4,308. Also notice that the number of rows read, 60,000 rows were read. So it had to read all of those rows, but it only returned in that data path, if you will, 4,300. The estimate was kind of close. Now let's look at the one with the scalar function that I built. Notice that it says 60,000 is estimated, 60,000 is actual, and it read all 60,000. So what happened here is that right here it says, I've got to go get all 60,000 rows, and then later, right over there, then I'm going to apply this black box that's a user-defined scalar function. So that path and that path has all of those 60,000 rows in it, whereas the other one above it, using the built-in function, it starts out right out with many fewer rows, 5,000 rows. That's referred to as predicate pushdown, meaning that the earlier you can filter, the better, because as soon as you filter, from then on, you're processing fewer rows. Better for performance. And there was something else I wanted to show on this, but I have to look at my note. Predicate pushdown, query, yes, okay. So each of these properties of the select statement, I have to open it up first. We also have query time stats that you can look at. If you right-click on the select, go to properties, and the built-in function has CPU time of 7. If I go to the other one, look at properties, open up the query time stats, CPU time of 274. Spent a whole bunch more time executing the whole query. User-defined scalar functions are evil. Often, not always, often you can convert them to an inline table-valued function using an apply operator. The SQL Server Optimizer can read into that and know what kind of cardinality it expects and do a much better job of optimizing. Can't always convert, but if you can, that's the way to go.
When
Yes.
When you use a scalar function in the select list and you're putting data in and you're reading tables to get the value that you want to return to be replaced in your select statement, if you're bringing back 100,000 rows, it's going to do 100,000 selects within that scalar function.
Yep. Scalar functions are not set-based. They're rebar. Anybody know who doesn't know what rebar is? Nobody raise their hand. Row by agonizing row. So no matter, the scalar function has to execute one at a time, and it brings a lot of performance to its knees. That's a big one as far as how bad of a performance hit you can have. Fortunately, I don't encounter it too often. Ignoring the transaction log. Every modification you make, every change that you make in a database, something has to go into the transaction log. Another aspect of the transaction log is that, other than some hardware workaround things, when you do statements, an update, insert, delete, the transaction log not only has to be modified in memory, it has to go out there to the disk before that statement is done. It can be a very significant part of any performance. So another little tidbit of information, I have a table and I have a column of first name. And let's say I've got a couple of rows in there where the first name is John. And I want to update every row in that table, setting the first name to John. When I execute that, it's going to update not only all the rows that aren't John, it's going to update those 2 rows or multiple rows that are John, and it's going to set them to John. In other words, if you do an update statement and change something to the same value that it already is, even though nothing really happens, the transaction log gets affected. The rows go into the transaction log. So, well, I'll show you what I've got. Turn off that. I am going to start by making a copy of the sales order header table into a temp table. Sales order header temp table is the name I'm going to call it. And then I'm going to update 200 rows in that table, adding a day to the ship date. I just want 200 rows to be different than the source table, the real table. So I'm just doing this to my temp table. And now I'm going to run this query, and let me walk through it a little bit. What I'm going to do is I have 2 updates that I'm going to do, and in between those, I'm going to take a look at the transaction log. And I'm going to, this fndb logs an undocumented function, and I can look at the size of the log, the number of rows, the record count in the log, and then I also take a look at the time. So I mark the starting point. This is how big the log is. Up there is a checkpoint to make sure I'm not changing anything other than my query. Then I'm going to do a statement, and then I'm going to take a look at the log again so I can see how many rows were added, how much bigger the log got. And then I'm also going to do the same thing again with a slightly revised query. And everything is the same except for the where clause. And you'll notice that I put in a filter that says I don't want to update a row if nothing is going to change. And since I'm updating the ship date, I'm going to compare the ship date of the source and the target. And because it's a nullable column, I have to consider the 3-state logic there. So in this case, those 200 rows won't be affected by this update statement. No need to. They're not changing. Exact same data. What am I doing? I'm saving an unnecessary use of the transaction log. So let's run this and see what it looks like. And I start up here. So the first one had a record affected 31,790 rows inserted into the transaction log. The second one affected 401. The size went up by over 3 meg with the first example, the other one by 0.04 meg. If I'm not changing anything, there's no reason to execute the update statement. How many of you are more of an data warehouse as opposed to an OLTP environment? How many? So the rest of you are OLTP? Okay. This is less effective in OLTP, but it still can be effective. In a data warehouse, you're retrieving from a source and you're always updating your data warehouse, your fact tables, your dimension tables. Often, if you're doing a full compare, 90+% of the source data hasn't changed, so why update everything in the target? So you say, okay, that's a nice thing, Vern, but I'm not going to write, I've got a table with 30 columns in my fact table. What's that where clause? I'm not going to have to write that thing, am I? Well, I'll give it to you. This, I can't get all of it on the screen, but this is a script, and right there at the top you enter in the schema name and the table name, and it will print out a where clause for you, including the logic of knowing whether or not a column is nullable, and because if it's nullable, you have to have the 3-state logic. Is it null and not null? Not null, null. And if it's not null, then it doesn't have to do that. And I put in sales order header, and let's run it, and I'll show you the output. There's your where clause. Is it long? Yeah. Is that bad? I think the savings far outweighs the negative side of having a long where clause. This simply makes sure that if you're going to do an update statement into a fact table, for instance, you're not going to update any rows that don't change. Transaction log will improve, your performance will improve. This will be downloadable on our website by this weekend. I don't think I can get to it tomorrow. Yes, I have. It's not 100%. It can have duplicates. I've played around with that. Yeah. I've also tried to use except, and yeah, I've kind of standardized on this. Row version is not 100%. Except can work just as effectively, but yeah.
Vern?
Yes.
You might want to mention that how we've implemented it in our work with our clients is we use Irwin for data modeling, and we will create a macro within Irwin that has this logic in it, and so it will have an update trigger that will create this automatically, and then we push that DDL out that has that where clause in it.
And in that case, the where clause in the trigger is to maintain our last modified timestamp column, because we don't want that incremented if nothing changed. If nobody knows, this is my beautiful wife, Debbie. If she's not following me everywhere, I'm following her everywhere. Ignoring data types. How many of you have seen my session on data types? A few. So I could spend a couple hours on data types. Data types are, in my opinion, are the most ignored area of SQL Server development, and they're so simple to do right, people just don't think it's important. Yes?
I recently annoyed our developer because there were so many implicit conversions in his stored procedure. It was just incredible. And you're probably going to show us an example, but it made the optimizer go crazy. It had like trillions of rows that it was trying to estimate because of that. And so, but I had to do all the work. I had to go through and actually write out and say, this is what's happening, this is where it's complaining about, before he would even, and finally it was enough to make him take it back. I know he's going to ignore it, but still, at least I guess I proved my point for what it was worth, so.
Implicit conversions. No, I don't have that as a sample. This is a brand new session, so it always starts out with things that you want to fix. My example is not as good as an implicit conversion. I'll probably change it. So having to do with implicit conversions gets into a couple of things. So first of all, who knows what sargeability is? Sargeability means a predicate is sargeable if the optimizer can get statistics or use an index on one of the columns in the predicate. And it's sargeable typically if the column is by itself on one side of the comparison operator. So if you have where this column is equal to 5, that's sargeable. If there's statistics or an index on that column, the optimizer has the option of using them. So put that little tidbit aside. Next thing is, did you know that SQL Server cannot compare two different data types? It can't say, is this integer the same as this varchar, varchar, whatever. It can't do it. But it is smart enough to realize they are different, and it has to convert one to the other before it does the comparison. And that conversion is an implicit conversion. It is behind the scenes, and you don't see it. When you look at your query, it looks good, but behind the scenes, it just did an implicit conversion. It took that one of those and said, cast this to something else to match that data type. That cast, if that's a column, that column is no longer by itself on one side of the comparison operator, which means that if there's statistics or an index on that column, it can't be used. So you have a question, I can tell, it's, but, yeah, okay. So again, if you have a predicate with two columns, is this column equal to that column? If they're not the same data types, you have a serious potential of performance problem because one of those two is going to get implicitly converted because you chose the wrong data type, and that implicit conversion is going to kill performance if there's an index or a statistic that the optimizer could use. I'm going to change my demo to do that, so I don't have it, but I had to explain it. So my demo is a little bit simpler, and it has to do with size, simply of size. I'm going to create two tables, decimal 1 and decimal 2, identical. They both have the same column, but one is a decimal 9.3 with a precision of 9 total number of digits, and the other one is a decimal of 29.3. Same data or same column names, other than the fact that the scale is different or precision is different. Then I'm going to insert into them 500,000 rows, exact same data. I often use a utility database, and in that I'll create many things, one of which is a numbers table or a tally table, some people refer to it. I think I have 20 million rows in that table. One column, number is the name of the column, 1 through 20 million. Many uses, demos is one of them. So I'm just going to insert 500,000 rows into both of those tables. So they're going to have the exact same contents in those two tables. And then I'm going to start by looking at the space used. So why do I look at the space used? When a query has to execute, there's several resources it uses, the CPU, sometimes network, the I/O subsystem. Generally, the I/O is considered the biggest hitter. If you can reduce the I/O of a query, you're going to probably get some noticeable improvement. So by looking at the space used, I'm going to see how much space would have to be read for various queries from that table. When I execute that, okay, that's what I want right there. So notice that I've got just under 7 meg for that one, and just under 13 meg for the other one. Almost twice as much space for the two tables that have the exact same data in them. So now that I have a reason to believe one will be slower than the other, turn on actual execution. I'm going to execute a query against both of them. Same exact query against the two tables. And the first thing I'll look at is the I/O. So if you're not familiar, my first thing that I look at is statistics I/O. You set statistics I/O on. Doing that gives you this kind of information when you execute a query, and it points out the logical reads, which to me is the most important. The logical reads is the number of 8K pages that had to be read by SQL Server in order to satisfy the query. So right there, the first query, 866, and the second one, 1608. So right there is almost twice as many 8K pages had to be read in the process of executing this query. So how does that relate to actual performance? Well, Oh, and actually, one other thing here. So here's the two queries in the actual execution plan. And again, this time, and I just know that it is, these estimates are relatively accurate. 41% of the time for the first one, 59% for the other. I don't have it here, but I ran them repeatedly with timestamps so I could see actual duration, and it was actually pretty close to 1.5 times faster or slower, depending which way you look at it. Yes?
29 digits and 9 digits, which
Yes.
is 3 to 1 to me, but all your other ratios have been 1.5 to 1 or 2 to 1. So it's
Because-
not like it takes twice, 3 times as much storage.
Because
The triangle.
IO is not the only thing, it's just usually the
Well,
biggest.
The blocks thing was only 50% larger. The box was 8 to 16 instead of 8
Oh,
to 24.
efficiencies of storing things within a page.
So some of the time, the 29 digits doesn't really take 29 digits. I mean, it doesn't take
Oh,
the
it will.
storage of
Well,
29
well, it's not 29 digits of storage, that's right. There's incrementing steps, 9, 19, and then 38. Is there 3 different?
Okay,
So
so it's because-
8 and 9 will have the same storage. As soon as you go to 10, it gets more storage.
So 29 isn't, okay.
I'll have to look it up to see the
But
exact
that's-
storage.
that's not the difference I expected.
All right, right, because of the incrementing storage, yep. Okay, we're down to, how am I doing for time? Oh, not using option recompile. So I have found 2 really good uses for option recompile. The first is, and again, these are my situations, and sometimes they'll apply to you, sometimes there's not the right choice for you, but just add it to your toolkit. So who knows what parameter sniffing is? Parameter sniffing is a pretty common problem. Within a stored procedure, one of the primary benefits of a stored procedure is that the first time you execute it, the optimizer comes up with a plan for the procedure, for every query in the procedure, stores those plans in cache, and then executes it. And then next time you run it, it doesn't have to go through that compile process to determine a plan. The plan has already been determined, and it's sitting in cache. So that is an optimization benefit. You eliminate that recompile every time. But sometimes that's a detriment, and that's where the negative aspects of parameter sniffing come in. Let's say that the first time I run it, I pass in a parameter to the stored procedure, and the optimizer says, oh, based on that parameter, this one query, I want to use a nested loop, because it knows what the parameter is. It's passed in when you first execute it. The second time you run it, you pass in a different parameter. That parameter ideally should never use a nested loop. It should be a hash match because of the cardinality from the table. But guess what? Nested loop is what's in the plan. That's what's going to be used. So sometimes you have a stored procedure that you would like to recompile every time. You don't want that plan to stay there because next time a different plan may be a better choice. One option for that is not option recompile, but with recompile at the stored procedure level. If you define a stored procedure with recompile, every single time you run it, the stored procedure will recompile. You will eliminate that problem. But let's say your stored procedure has 100 queries in it, and only 1 or 2 of them are affected by this parameter sniffing. Well, when you do the with recompile, you're recompiling everything every time. That's an unnecessary performance hit. We also have an option recompile, which is done at the statement level. And what that says is that this one statement, blah, 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 option recompile, when it executes, it executing the whole stored procedure. When it gets to that query, even though it's reading everything out of the plan cache, it says, oh, this one says option recompile. Stop, recompile again that one query, now using the new parameter, and then try it again, and then continue on. So within a stored procedure, if you have a query that is giving you problems because of parameter sniffing, this is one, and I think a pretty decent solution to that problem. Just as a point out a little bit more, oh, yes, go ahead.
One thing I want to note with that is if the query you're doing that on is executed maybe thousands of times each second, it's going to really drive up the CPU.
This is absolutely, if you're doing queries, executing queries many times a minute, many times a second, this is not a good choice. This is a great thing to use in an in a data warehouse environment where you have a stored procedure that might take 5 minutes or an hour to run. You run it at night or whatever. It's a big stored procedure. It takes a while to do. The compiling part then is a small percentage of the overall duration of the statement. If you've got an OLTP environment, rarely would you want to use that. Not never, but rarely, because then the query that takes 5 milliseconds just took 50 milliseconds because of the other 45 milliseconds for the compile. So be cautious in an OLTP environment. Here's another little thing. So within a stored procedure, you might have a temp table. So you create the temp table, you populate within your stored procedure, you populate it, and then you reference it. So think about how the compile process of a stored procedure runs. The first time you execute it is when it gets compiled. Okay, you pass in a parameter or two, it doesn't matter. You execute it, the optimizer says, okay, I've got to figure out a plan for everything in here. Here's the first statement, okay, I'm going to do it that way. Here's a statement that loads and creates a temp table, that's trivial, I created it. Now a statement that populates the temp table, okay, I'm figuring out how to do that. And then you have a query that references the temp table, that joins the temp table with something else. This compiling process takes place before the procedure executes. That temp table has nothing in it. It doesn't even exist. The optimizer knows that it will exist, but it has no idea what is going to be in it when it actually runs. So how does it know? Is it going to get 1 row or 1,000,000 rows? It doesn't, so it has to guess. Guesses are not good. So that query after the temp table that references the temp table, if you have that query and say option recompile, remember what happens when it runs. First of all, I compile everything. Then I execute this. I create the temp table. I populate the temp table. This is all, the plan is already in cache. I'm executing it now. And then I get to this statement that has option recompile. Stop right there and recompile that statement. I have contents in the temp table. The optimizer can create statistics on it right then and there and come up with a much better plan. So a general rule, again, avoided in OLTP, but for data warehouse environments, a general rule is if you have a query that references a temp table that is populated within the stored procedure, or if you have a query that references a variable that is created within the stored procedure, not a passed-in parameter, that's totally different, a variable, same thing, try option recompile. You just might suddenly get some great performance improvement. And I have a couple of, let's see, yes. So I have 2 stored procedures. This one is, I'll go to the other one. Here's my parameter sniffing query. So all I'm doing here is I'm doing an aggregate, the sum of the order quantity from fact reseller sales, where this promotion key is equal to a certain input parameter, okay? It's passed in promotion key. So the first time I run this, I'm going to get a plan for that query. It's going to go into cache. From then on, as long as it stays in cache, that same plan's just going to get reused, whether it's a good plan or not. My second stored procedure, exact same thing, but I added an option recompile. So now, even though it's going to compile the stored procedure, when it goes to execute it every time it executes, it's going to recompile that one statement. And again, OLTP, that may not be a good choice, but in a lot of data warehouse, this will fix a lot of problems. So that's our 2 stored procedures. So let's see what they look like in action. Turn on, I'm going to free proc cache, which if you ever read much about free proc cache, it's strongly encouraged to go out and do that in your production environment every day. Hourly? Okay. Free proc cache throws everything out, all your plans out of cache. So the next time every procedure runs, it's got to be recompiled, which remember the main one of the main values or benefits of a stored procedure is it only gets compiled that first time. So you're eliminating that benefit if you do free proc cache. Okay, nothing in my cache, and I showed you, let's see, so what I'm going to execute here is the non-fixed version, and I'm going to execute the stored procedure twice. The first time with a promotion key of 5, and when I execute that, it's going to come up with a plan based on promotion key of 5, with whatever distribution of the data is for promotion key 5. Then the plan's in cache, and then I'm going to execute it a second time with a different parameter, but the plan's going to be reused. So I'm going to execute that one, and let's see, what we have here is, there's just a little bit of difference there. Now the second execution of the stored procedure will be bigger because it's going to return many more rows. But just remember 172,000 pages had to be read. Why so many pages? Well, notice that the first plan appropriately came up with a nested loop. We had very few rows coming out of here. Let's see how many rows. Hover over that. We had 2 rows coming out of it. Okay, so 2 rows, often that means a nested loop is a good choice. Nested loops in the plan, in cache, that's going to get reused over and over again. The second one, notice the estimated number of rows. It's the same plan, so their estimate didn't change. Estimated 2, actual 57,000. It still is using a nested loop. For 57,000 rows, that's probably not a good choice. But it's stuck. A nested loop is what it is, and because it did this, looped around that 57,000 times, that's why it read so many pages out of RAM. It read it over and over and over and over again. So now I'm going to do the exact same thing with the fixed stored procedure. Remember, the only difference is I had option recompile on the query. And when I execute that, when I look at messages, still higher, as I said it should be, but it's not 172,000, it's 1,600. Obviously much faster. And when we look at the plan, we will now see that because the second parameter would work better with clustered index scan instead of a nested loop, it chose a better plan. Different plan, much improved. Not all queries are subject to parameter sniffing problems, but every once in a while you run into one and they are a problem. What's really insidious about it is remember that the plan that you get is what you get the first time you run it. So I've got this plan in cache and it seems to be a good one. You know, it seems to work fine with all of my examples. Some of them aren't as good as maybe they could be. And then somebody comes along, some developer, and he writes this query that fills up the tempdb, flushes everything out of the cache, and all of a sudden, the next time you execute it, you get a brand new plan. And now, by chance, it's not a good one. So what worked perfectly forever was never touched. Nobody ever touched the data. Nobody touched the stored procedure. Somebody did something over here, and all of a sudden, it goes in the toilet for performance. It happens. Yes?
Whenever new applications are deployed, what's the first thing that happens? Test data comes in, and they use edge cases. So they put in the plan cache full of crap plans. This is a chance where right after they run their test, do a free proc cache.
Yep. Okay. Any questions on that one? Down to my last one. Sargeable. I already mentioned what Sargeable was, and it's my number one because I encounter it often, and the effects of doing it right can be very significant. And again, to repeat, a Sargeable predicate is when a column is by itself on one side of the comparison operator. Not always doing that will not always improve the performance, but every once in a while you find one that it should be using a statistic or index and it's not, and changing it changes everything. Sargeability is really simple to implement, to do it right. And I have two examples to point out sargeability. So the first one, these two queries are logically identical. I have a variable integer, give it a value of 2. Query from my numbers table where the column, this is a column, is less than that variable plus 1. So where the column is less than 3, so I'm going to return a 1 and a 2. Logically equivalent down here, I say where the number minus 1 is less than the variable. So again, I will return a 1 and a 2. Identical logically. I just moved that plus 1 to the other side and made it a minus. Mathematically, that's, I can't remember what law that is. Notice here that the number column is not by itself on one side of the comparison operator. That's the only difference. It's not by itself. And because of that, statistics and indexes can't be used. 3 reads versus 32,000 reads. Only because I moved that column by itself or not by itself on one side of the comparison operator, made it sargeable. And if we look at the plans, generally speaking, a seek is better than a scan. And just the size of that arrow indicates how many rows I have to process before I can filter out the ones that I want. Clearly different, and in fact, that's a relatively accurate, as you saw from the I/O, that about 0% of that batch was spent executing the first query. Huge difference. My other example, and this one is extremely close to one that I encountered at one of my clients. And this client had a view, and in the view predicate had where this string, where the left 3 characters of the string were equal to ABC or something. And that was in a view that was used, referenced in a lot of stored procedures. That was not sargeable because it was using the left function encasing the column, and that's very much what this was. Left last name equal to sim, whereas a last name like sim with a percent sign, the wildcard. Logically equivalent, but this one is sargeable. As a result, this one can use an index or statistics. That one can't. When I fixed that, by the way, several people said, wow, this job here, this thing, so many things ran faster. And it was all because I changed that. I changed it from that to that. That's all I did. These are so simple to find. And when I execute that and look at some numbers on it, physical reads 3 versus 108. And execution plan, index seek, and index scan. Come here. And I haven't used this thing, but I've got to use it. See, there's the index seek, and there's the index scan. I've got to figure out how this thing's going to work well.
That was a waste of money.
Says my wife. So, any questions? I will repeat. I've got cards up here. Do not hesitate to pick up a card. Do not hesitate to send me an email. More than happy to talk about issues, learn stuff, and share information. So please. Thank you.